Hello everyone, welcome back to our lecture on computer programming for engineering applications. Alright, let's recap what we've covered before diving into today's topic. So, in our previous sessions, we explored how programs become more organized and easier to manage when we use functions. So think of function as reusable blocks of code that helps us avoid repeating ourselves. So these functions can be either iterative, meaning they use loops, or recursive, or meaning they call themselves. We also discuss how arguments are passed to functions, and this can be done either by reference or by value. And passing by value means that a copy of the variable is sent to the function, while passing by reference means that the functions get direct access to the variable itself. And now today's we're going to discuss about organization and pointers in C. As we progress, you'll gain the ability to seamlessly declare both local and external variables in your programs, ensuring clarity and efficiency in your code, and we'll delve into understanding the scope of variables within their respective blocks, empowering you to control accessibility and streamline your code structure. Additionally, we'll tackle the often intimidating concept of pointer variables, and by the end of our time in this video, you'll feel more comfortable assigning values to pointers and utilizing them as arguments in functions. And this will open up new possibilities for your programming effort. So in programming, when we talk about local variables, we refer to the variables that are declared within the body of a function. This means that they're only accessible within that specific function. So for instance, take a look at this function named SUMDigits in the slide. So inside this function, there's a variable called sum, which is declared as an integer and initialized to 0. This variable sum is what we call a local variable because it exists only within the SUMDigits function. And within the function, we perform a certain operation using sum, which in this case involves summing up the digits of a number n. And once the operation is complete, the function returns the value of sum. And when we talk about local variables, there are some default properties we need to understand. Firstly, local variables have what we call automatic storage durations. This means that the memory space for these variables is allocated automatically when the function containing them is called, and it's deallocated when the function finishes its execution and returns. So in simple terms, they come into existence when the function starts and disappear when it ends. Secondly, local variables have what's known as block scope. This means that they're visible and accessible from the point where they're declared until the end of the function in which they are declared. So any code within the function can access and manipulate these variables, but once we leave the function, they're no longer accessible. And when we include the keyword static in the declaration of a local variable, it changes the storage duration of that variable. So instead of having automatic storage duration like regular local variables, a static local variable has what we call static storage duration. This means that a static local variable is allocated a permanent storage location in the memory. Unlike automatic variables that are created and destroyed each time the function is called, a static local variable retains its value throughout the entire execution of the program. So it will maintain its value even after the function finishes the execution and retains it for the duration of the program's execution. Now take a look at the example here we have in the slide, the function f. So inside this function, there's a variable I declared as static. This makes I a static local variable. And it's important to note that despite having a permanent storage location, A static local variable still maintains block scope. This means it's only visible and accessible within the function in which it's declared, and it's not accessible to other functions. Now let's explore the parameters of function in C programming. So parameters of a function share similar properties with local variables. They also have automatic storage duration and block scope. This means that, like local variables, parameters are created and destroyed automatically when the function is called and finished executing, and they're only visible when the function in which they're declared. Now, when a function is called, each parameter is automatically initialized. This means that it's assigned the value of the corresponding argument that is passed to the function during its invocations or its call. So when you call a function and pass arguments to it, those arguments are used to initialize the parameters of the function. And when we talk about passing information to a function, one common method is by passing arguments. However, there's another way functions can communicate, and that's through external variables. So external variables are those that are declared outside the body of any function, and they exist in a scope that extends throughout the entire program, making them accessible from any function within the program. So sometimes external variables are also referred to as global variables because of their broad scope and accessibility. And using external variables allows functions to share data and information more directly without the need to pass argument explicitly. However, it's important to use them judiciously and consider their implication on program structure and readability. And external variables share some important characteristics. Firstly, they have static storage duration, similar to the static local variables. This means that the external variables retain their values throughout the entire execution of the program. And secondly, external variables have what we call file scope. This means that they're visible from the point where they're declared until the end of the file in which they're declared. So any code within the same file can access and manipulate these variables. And extra variables can be quite convenient in certain situations, and they're particularly useful when multiple functions need to share a variable, or when a few functions need access to a large number of variables. So in such cases, using extra variables can simplify the communication between functions and streamline the program structure. However, it's important to consider the drawbacks of relying too heavily on external variables. So in most cases, it's better for functions to communicate through parameters rather than by sharing variables. And this approach promotes more modularity and encapsulation, making the code easier to understand, to maintain, and to debug. And one of the potential drawbacks of external variables is that if we make changes to them during program maintenance, such as altering their type, we'll need to carefully review every function in the same file to understand how these changes affect them. And this can be quite a time-consuming and error-prone process, particularly in very large programs. And furthermore, if an external variable is mistakenly assigned an incorrect value, it can be challenging to identify which function is responsible for the error. And this can lead to debugging difficulties and inefficiencies when we are trying to troubleshoot the issues within our code. And it's important to avoid using the same extra variable for different purposes across different functions. For example, suppose several functions require a variable named I to control a for loop, And some programmers may be tempted to declare I just once at the top of the program rather than declaring it within each function that uses it. However, this practice can be misleading. It may give the impression that the uses of I are related, when in fact they serve different purposes in different contexts, and this can lead to confusion for someone reading the program later on, as they may incorrectly assume a connection between the different uses of I. And to maintain the clarity and avoid misunderstandings, it's best to declare variables within the smallest scope possible and give them meaningful names that reflect their purpose within each function. And when using external variables, it's crucial to give them names that accurately reflect their purpose or function within the program. Meaningful names make the code easier to understand and maintain, as they provide clarity about the role of each variable. And in contrast, local variables, which are declared within a specific function and have limited scope, may not always require such descriptive names. For example, it's common to use simple names like I for control variables in for loops. And in these cases, it can be challenging to think of a more meaningful name that adequately describes the variable's purpose within the context of the loop. However, even though local variables like I may not have highly descriptive names, it is still important to use meaningful names for external variables to ensure clarity and readability for our program. And external variables, when used appropriately, can facilitate communication between functions and simplify the sharing of data. However, misusing them by making variables external when they should be local can lead to frustrating bugs and unexpected behavior in our programs. And now let's see this example code intended to display a 10 times 10 arrangement of an asterisk. And the code defines a variable I outside any function, making it an external variable. And the two functions, print one row and print all rows, are then used to print the rows of the asterisk. However, there's a problem in the implementation. So instead of declaring I as a local variable within each function, it's declared as an external variable. And as a result, when print all rows call print one row, it alters the value of I, causing the value of I to be incremented to 10. So instead of printing 10 rows as intended, print all rows only prints one row, because in the next iteration of the print all rows, the value of I will already be 11 and the loop already stopped. And this example highlights the importance of carefully managing variable scope and avoiding the misuse of external variables. So in section 5.2, we have encountered compound statements in the form of curly braces statements, where multiple statements are enclosed within curly braces. However, C allows compound statements to contain not only statements but also declarations. And this means we can include variable declarations within a compound statement. And when a compound statement contains both declarations and statements, it is referred to as a block. So in other words, a block is a group of statements and declarations enclosed within curly braces, and blocks are commonly used in C to define the scope of variables. And by declaring variables within a block, we can limit their visibility and ensure they are only accessible within that specific block. And this helps us in organizing our code and preventing unintended interactions between variables in different parts of our program. And in this example, we have an if statement that checks if the value of variable I is greater than the value of the variable j. And if this condition is true, the block of code within the curly braces is executed. And inside the block, we have multiple statements that perform a swap operation on the values of variable I and j. And we declare a temporary variable temp to hold the value of I before swapping it with the value of j. And this allows us to safely exchange the values of the two variables. And the entire block, including the variable declaration and the swap statements, is enclosed within the curly braces. And this block defines a specific scope where the variables temp, I, and j are accessible and can be manipulated. And blocks like this are commonly used in C to group related statements and declaration together. And this will help you define a clear scope for variables and facilitating code organization. And when we declare a variable within a block in C by default, it has automatic storage duration. This means that the memory space for the variable is allocated when the block is entered and deallocated when the block is exited. So in simple terms, the variable exists only within the block and is created anew each time the block is entered. And additionally, variables declared within a block have block scope. This means that they can only be referenced and accessed within the block in which they are declared. And once we exit the block, the variable goes out of scope and cannot be used elsewhere in the program. However, it's worth noting that we can declare a variable within a block as static to give it static storage duration. This means that the variable retains its value throughout the entire execution of the program, similar to the global variables. However, the scope for that static variable remains limited to the block in which it is declared. And in C programming, the body of a function is essentially a block. So this means that we can declare variables and execute statements within the function body just like we would within any other block of code. And blocks are especially useful inside function bodies when we need to use temporary variables for a specific task. And declaring variables within blocks allows us to keep the function body organized and efficient. And there are several advantages to declaring temporary variables within blocks. So firstly, it helps avoid cluttering the declarations at the beginning of the function body with variables that are used only briefly. And by declaring these variables within blocks closer to where they are needed, we keep the code more concise and more focused. And secondly, declaring variables within blocks reduces the likelihood of name conflicts. And since variables declared within blocks have limited scope, they're less likely to clash with variables of the same name in other parts of the program. And additionally, starting from C99, the language allows variables to be declared anywhere within a block, not just at the beginning. And this will provide you with more flexibility and allows for more readable and more maintainable program. In a C program, it's possible for the same identifier to have multiple meanings or interpretation in different parts of the program. So C's scope rules play a crucial role in helping both the programmer and the compiler determine which meaning of an identifier is relevant at any given point in the program. And one of the most important scope rules in C programming is as follows. So when a declaration inside a block names an identifier that's already visible, the new declaration temporarily hides the old one and the identifier takes on a new meaning within that block. This means that the new declaration overrides the previous one within the scope of the block. However, it's essential to note that this change in meaning is temporary and limited to the block in which the new declaration is made. And once the block is exited, the identifier regains its old meaning, and any subsequent references to it will refer to the original declaration. So in the next slide, we're gonna have several examples of different meanings for identifier I. Now let's see the next slide. So in the example provided, the identifier I is used for different declarations, and for every declarations it have different meanings. So the first one, in declaration 1, I is declared as a variable with a static storage duration and file scope. This means that its value persists throughout the entire execution of the program, and it can be accessed from any function within the file where it is declared. And in the declaration 2, I is declared as a parameter with a block scope. This means that it is only accessible within the block of code where it is declared. And in this case, it's the body of a function. And in the declaration 3, I is declared as an automatic variable with block scope. And this means that it is a local variable that is allocated and deallocated automatically each time the block in which it is declared is entered and exited. And similarly, in the declaration 4, I is also declared as an automatic variable with block scope. And the scope rows enables us to determine the meaning of I each time it's used within the program. And the rows in the example indicate the scope of each declaration. This will help us understand which I is being referenced at any given point in the program. So like we've known, when we're setting up a C program, it's important to consider its major components. So firstly, we have preprocessing directives such as the include and define, and these directives are used to include header files and define symbolic constants or macros, and they're processed before the compilation. And next we have the type definitions. This allows us to create a new data types or aliases for existing ones, and this function will enhance our code readability and our code organization. And then there are also declarations of extra variables, and the statements declare variables defined in other source files and accessible throughout the program. And we're typically using the extern keyword. And then we have function prototypes, and these declarations provide information about a function's name, their return type, and parameters before its actual implementation. And this will enable the compiler to perform the type checking. And finally, we have the function definitions. And this section contains the actual implementation of the functions, specifying their behavior and their logic. So when we are organizing a C program, it's essential to understand the rules governing the order of its components. So firstly, a preprocessing directive such as include or define doesn't take effect until the line on which it appears. This means that the preprocessor processes directives in the order they appear in the code. And secondly, a type name cannot be used until it has been defined. This means that if you're using a custom data type, you must define it before using it in your program. And similarly, a variable cannot be used until it has been declared. So in other words, you must declare a variable before you can use it. And furthermore, it's a good practice to define or declare every function before its first call. and this helps avoid issues with undefined functions and ensures that the compiler knows about the functions you intend to use. And in C99, this practice is not just recommended, but it's required. And C99 standard mandates that function must be defined or declared before they are called in the program. And there are also several approaches that we can take. And one of the most common organization method is as follows. So firstly, we include any necessary header files using the include, and then we ensure that the necessary libraries and resources are available for our program. And next, we define any symbolic constants or macros using the define directives, and this will allows us to create aliases for values or expressions that we'll use throughout our program. And following that, we define any custom data types or aliases for accessing types using the type definitions. And this will help us improve our code readability. And then we declare any external variables that are defined in other source file that are needed in our program using declarations. And after that, we provide prototypes for any functions other than main that will be used in our program. As prototypes inform the compiler about the function's name, return types, and their parameters. And next, we define the main function, which serves as the entry point of our program. And finally, we define the implementations of any other functions used in our program. And these implementations provide the actual logic and behavior of the function that we've declared in our prototype before. And when we're organizing C programs, it's so beneficial to include a comment before each function before function definition. And these comments provide essential information about the functions proposed, their parameters, their return value, and any side effects it may have. And in each of the box comment, you can consider including the following information. First is the name of the function, and this will help us to identify the function and distinguish it from others in the program. And second one is the purpose of the function. This one is used to describe what the function is intended for, what is trying to accomplish, and or the problem it solves within the program. And the third one is the meaning of each parameter. And this one should explain the significance of each parameter passed to the function, including its data type and their expected usage. And the fourth one is description of the return value, if there are any return value. So it will specify its purpose and any conditions under which it may vary. And the fifth one is description of side effects. And in this part, we should mention any side effects that the function may have, such as modifying external variables or performing actions beyond its primary purpose. And by including all of these box comments before each function's definition, we provide valuable documentation that enhance our code readability, maintainability, and make it easier for others to understand our program. Here we have a little bit of exercises that you can do on your own, and if you have any difficulties, you can just reach me out or just reach out to Pawiratu. Okay, so what makes C special compared to other modern programming languages such as Python, Java, or JavaScript? So C gives us, the programmer, the ability to manipulate variable through their memory address, or what we call pointers. And to understand pointer variables, it's crucial to know the representation at the machine level. So in modern computers, the main memory is segmented into bytes, with each byte capable of holding 8 bits of information. And these bytes are assigned unique addresses, which serve as identifiers for accessing them. So imagine memory is a vast array of boxes, and each labeled with a unique address. And each box or each byte can store a small piece of information. And these addresses enable the computer to locate and manipulate data stored in memory efficiently. And pointer variables essentially hold these memory addresses, and they point to the location of data in the memory rather than holding the data itself. And by understanding this fundamental concept, we can unlock the power of pointers in C programming. And when considering memory, we can imagine it as a sequence of bytes, and each with its unique address. And these addresses serve as identifiers, allowing us to access and manipulate data stored in memory. And if there are n bytes in memory, the addresses are essentially numbered that range from 0 to n-1. So this means that the first byte in memory is address 0, and second byte as 1, and so on up to n-1, which is the last byte in memory. And by understanding this concept, we can visualize memory as a linear array of bytes, with each byte accessible via its unique address. And this understanding forms the foundation for working with pointer variables in C programming, as pointers essentially hold and manipulate these memory addresses. In a program, each variable is stored in a memory, occupying one or more bytes of memory space, and the address of the first byte allocated to a variable is referred to as the address of the variable. So consider the following illustration. If the variable I is allocated memory space starting from address 2000, then the address of the variable I is said to be 2000. This means that the memory address 2000 points to the beginning of the memory space allocated for the variable I. And visualizing this concept helps us understand how variables are stored and accessed in memory. And pointers in C programming allows us to work with these memory addresses, enabling us to manipulate data and create more dynamic and efficient programs. And in C programming, we have the concept of pointer variables, which are special variables used to store memory addresses. And when we store the address of a variable, let's say I, in a pointer variable, for instance, P, we say that P points to I. Essentially, P contains the memory address where the variable I is located in the memory. And to illustrate this concept visually, imagine I as a box in a memory, and P as an arrow pointing to the address of I. And in this graphical representation, P serves as a reference to the location of I in memory. And by using pointers, we can indirectly access and manipulate data stored in memory, allowing for more dynamic and versatile programming approaches. So in C programming, when we declare a pointer variable, its name must be preceded by an asterisk. This asterisk indicates that the variable is a pointer. So for example, consider the declaration integer asterisk p. Here p is a pointer variable capable of pointing to objects of type integer. And it's important to note that we use the term object instead of variable because p might point to an area of memory that doesn't necessarily belong to a variable. So in other words, P can point to any memory location whether or not it contains a defined variable. And understanding pointer variables declarations is crucial for effectively working with pointers in C programming. And by properly declaring pointer variables, we can manipulate memory addresses and access data stored in memory, enhancing the flexibility and efficiency for our programs. Okay, so when we declare pointer variables in C, we can include them in declarations along with other variables. So for instance, here we can see in the slide, here we declare multiple variables including the integers, which is the I and j, arrays, the a and b, and then the pointer variables p and q. And it's also important to note that C requires that every pointer variable point only to objects of a particular type, also known as the reference type. So, for example, the integer p asterisk p points only to integers, and the double pointers q point only to doubles, and the character pointer r only points to characters, and each pointer variable is associated with a specific data type, and it can only point to memory locations that store values of that type. However, there are no restrictions on what the reference type may be, and pointers can point to any data type, including user-defined types, structures, or even other pointer types. So in C, we have specialized operators designed specifically for working with pointers. Firstly, to find the memory address of a variable, we use the ampersand operator or the and symbol, which is called the address operator. This operator allows us to retrieve the memory address where a variable is stored in the computer's memory. And secondly, to access the value stored at the memory location pointed to by a pointer variable, we use the asterisk operator, also known as the indirection operator. And this operator, represented by the asterisk symbol, enables us to dereference a pointer and retrieve the value it points to. And by using this address and indirection operators, we can effectively manipulate memory addresses and access the data stored at those addresses using pointers in C. And when we declare a pointer variable in C, such as integer pointer p, we allocate memory for the pointer itself, but it doesn't initially point to any specific location in memory. So in other words, the pointer p doesn't have a defined value or address assigned to it at this stage. And this is a crucial point to understand. By declaring a pointer variable, it just reserves a memory space for it, but it doesn't automatically make it point to any particular object or variable in memory. And therefore, it's essential to initialize the pointer before attempting to use it. And initializing the pointer involves assigning it to the memory address of a specific variable or object. And this ensures that the pointer points to a valid memory location. And this will allow us to safely dereference it and access the data stored at that address. And failing to initialize a pointer before using it can lead to unpredictable behavior and potential errors in our program. So you should always remember to initialize pointers before using them to avoid any unexpected results in your C program. And to initialize a pointer variable in C, one common approach is to assign it the memory address of a specific variable. So for instance, here in this slide, in this code snippet, we have declared an integer variable I and a pointer variable p. And to initialize the pointer p, we use the address operator ampersand followed by the variable name I to obtain the memory address of I. And by assigning this memory address to the pointer variable p, we effectively make p point to the variable I. So in other words, p now holds the address of I, enabling us to access and manipulate the data stored in I indirectly through p. And also it's possible to initialize a pointer variables at the time of their declaration. So for example, we have this code snippet in the slide, the integer I and integer pointer p equal to %I. In this case, we declare an integer variable I and simultaneously initialize a pointer variable p to point to I. This is achieved by using the address operator ampersand to obtain the memory address of I and then assigning it to the pointer variable p. And furthermore, we can combine the declaration of I with the declaration of p in a single line, like the one in the bottom. Here both I and p are declared in the same line, and p is initialized to point to I using the address operator or the ampersand. And this approach offers a concise way to declare and initialize pointer variables, making the code more readable and more efficient. And once a pointer variable points to a specific object in memory, we can use the indirection operator or the asterisk to access the value stored in that object. So for example, if we have a pointer variable p pointing to an integer variable I, we can print the value of I using the following code in the slide, the first code that we have here in the slide. Here the asterisk operator, the reference is the pointer p, and this allows us to retrieve the value stored in the memory location pointed to by p, which is the value of I. Additionally, applying the address operator or the ampersand to a variable produces a pointer to that variable. And conversely, applying the indirection operator or the asterisk to a pointer takes us back to the original variable. We can see the example here in the bottom of the slide. In this example, the ampersand I produces a pointer to the variable I, and then the asterisk, the reference is this pointer, resulting in the value of I. Therefore, the statement j equal to asterisk ampersand I is equivalent to j equal to I. Understanding how to use this operator allows us to access and manipulate the data indirectly through the pointers in C programming. And when a pointer variable p points to a specific object, using the indirection operator or the asterisk on p allows us to access the value stored in that object. So in essence, the asterisk p serves as an alias for the object to which p points. So for instance, if p points to an integer variable I, then pointer p represents the value of I. This means that the pointer p and I are interchangeable and they hold the same value, and changes made to one will reflect on the other. Here in this slide, this shows the interaction and the interchangeability between p and I. And applying the indirection operator or the asterisk to an uninitialized pointer variable can lead to undefined behavior. So we can see here in the example in this slide, the first one, here p is a pointer variable that has not been initialized to point to any valid memory location. And attempting to dereference such pointer using the asterisk operator leads to undefined behavior. This means that the program's behavior becomes unpredictable and it may result in crashes, errors, or unexpected outputs. And similarly, assigning a value to the object pointed to by an uninitialized pointer is also dangerous. For example, we have the code snippet here in the bottom of the slide. In this case, the pointer p attempts to assign the value 1 to the memory location pointed to by p. However, since P has not been initialized, it does not point to any valid memory location, and as a result, this operation also leads to undefined behavior. That's why it's essential to always initialize pointer variables before dereferencing them or assigning any values to the objects they point to. And this will ensure that the pointers point to valid memory locations and prevent undefined behavior in your programs. And also we can use the assignment operator or the equal symbol to copy pointers of the same type. You can see the example here in the slide. Here we have two integer variables I and j, and along with two pointer variables p and q. And in the example in the bottom of the code, in the bottom of the slide, we assign the address of variable I to the pointer variable p using the assignment operator and the address operator. And after this assignment, the pointer p holds the address of variable I. This allows us to access and manipulate the values stored in I indirectly through p. This one is another example of pointer assignment. Here in this scenario, we are assigning the value of pointer p to pointer q using the assignment operator. After this assignment, both q and p now point to the same memory location. In other words, they hold the same memory address, and this means that any changes made through q will also affect the same memory location as p, and vice versa. And now let's consider a scenario where both pointer variables p and q point to the same object I. In such case, we can modify the value of I by assigning a new value to either pointer p or pointer q. So for instance, here in the slide, here the pointer p equal to 1 assigns the value 1 to the memory location pointed to by p, which in turn modifies the value of I. And similarly, the pointer q equal to assigns the value 2 to the memory location pointed to by q, also affecting the value of I. And it's important to distinguish between two different operations, q equal to p and pointer q equal to pointer p. The statement q equal to p is a pointer assignment where the value of pointer p is assigned to pointer q. This means that both q and p will point to the same memory location after this assignment. On the other hand, the pointer q equal to pointer p is not a pointer assignment. Instead, it is an operation that dereferences both pointers p and q to access the values stored at the memory locations they point to. Then the value stored at the memory location pointed to by p is assigned to the memory location pointed to by q. And it's crucial to understand this distinction to avoid confusion and unintended behavior in your code. Next, we'll explore an example statement to illustrate the effect of pointer q equal pointer p. Now, let's break down the example statement here that we have on this slide. So firstly, p equal to ampersand I assigns the address of variable I to pointer variable p, and similarly q equal to ampersand j assigns the address of variable j to pointer variable q. And then the I equal 1 sets the value of variable I to 1. And then finally, pointer q equal to pointer p dereferences both pointers p and q, meaning it accesses the values stored at the memory locations they point to. It assigns the value stored at the memory location pointed to by p to the memory location pointed to by q. So let's imagine this with an example. Let's assume I initially holds a value of 1 and j holds some other value. So after the execution of the given statements, the value of I, the q first, the p points to the memory location of variable I, and then q points to the memory location of variable j, and the value of I becomes 1. And then the value of variable j, pointed to by q, becomes the same as the value of variable I, which is pointed to by p, which is 1. So in chapter 9, we have encountered a challenge while attempting to create a decomposed function that could alter its arguments directly. However, by passing a pointer to a variable instead of the variable's value itself, we can overcome this limitation and rectify the issue with the decomposed function. Now, let's delve deeper into this concept. So, when we pass a pointer to a variable as an argument to a function, we essentially provide the function with the memory address where that variable is stored, and consequently, the function can directly access and modify the content of that memory location, effectively altering the original variable's value. And this approach proves especially useful when we need a function to make changes to the variables defined outside its scope, or when we desire to conserve memory by avoiding an unnecessary duplication of variable values. And now let's redefine the decompose function to accommodate pointers as arguments. So this revised version of the functions will take 3 parameters, a double value x and 2 pointers, one for the integer part and another for the fractional part, and inside the function we'll calculate the integer part of x and assign it to the memory location pointed to by integer part, and similarly we'll compute the fractional part of x and store it in the memory location indicated by fractional part. And now let's consider the function prototypes for decompose. We have two possible options. First, prototype specifies the parameter names explicitly, providing clarity about the purpose of each parameter, and the second prototype omits the parameter names and only includes their data types and pointer symbols, which is a more concise but is equally valid representation. And both of these prototypes convey the same information about the function's parameters, and they're both interchangeable based on personal preference or the conventions that you use. And when we call the decompose function, we provide it with 3 arguments: the double value, the pi, and the addresses of the 2 variables I and d, denoted by $i and $d respectively. So upon executing the function, the memory addresses of I and d are passed to the decompose function, which in turn receives them as pointers. And inside the function, these pointers are used to access the memory locations where I and d are stored in the calling function. And as a result, the parameter integer part points to the memory location of variable I, while the parameter fractional part points to the memory location of variable d. And this enables the decompose function to modify the values stored in I and d directly using the dereferencing operators asterisk to access the variables they point to. And in the decompose function, the first assignment takes the double value x and converts it to a long integer type, and this converted value is then stored in a memory location pointed to by the integer part pointer. And to clarify, when we say the object pointed to by integer part, we're referring to the variable whose address is stored in the integer part pointer. So in other words, integer part points to a specific memory location where a long integer value will be stored. So in the decompose function, the second assignment calculates the fractional part of the double value x by subtracting the integer part stored in the memory location pointed to by integer part pointer from the original value of x. And this calculated fractional part is then stored in the memory location pointed to by the fractional part pointer. And to clarify, when we say the object that fractional part points to, we mean the variable whose address is stored in the fractional part pointer. It's the same with the previous integer part. So in essence, the fractional part points to a specific memory location where the fractional part of the value will be stored. Also, if you have noticed it or not, but also this kind of function, the arguments provided are also pointers. So for instance, let's consider the variable I of type integer we have here in the slide. So when we're using scanf to read an integer value into I, we pass the memory address of I to scanf using the ampersand operator. And this is crucial because scanf requires the address of the variable where it should store the value entered by the user. And without the ampersand operator, the scanf would receive the value of I itself, which will not allow it to store the user input in the correct memory location. And in the case of scanf, while it's true that its arguments must be pointers, also it is also important to note that not every argument requires the ampersand operator. So let's consider an example where we have an integer variable I and a pointer variable p pointing to it. In this scenario, when we want to read an integer value into I using scanf, we simply pass the pointer variable p itself as an argument without the ampersand operator. And when we try to use the ampersand operator in this context, it will be incorrect as it would result in passing the address of the pointer variable p rather than the address of the variable I. So when we call a function that expects a pointer as an argument, failing to pass a pointer can lead to a serious issue. So let's see here we have the function decompose. So if we forgot to include the ampersand operator when passing argument, such as the one that we have here in the slide, where I and d are variables, the function will receive the values of I and d instead of their address. And as a consequence, when decompose tries to store values in integer part pointer and fractional part pointer, it will attempt to change the unknown memory locations instead of modifying the intended variables I and d. And next, we're gonna have an example program called max minimum C, which helps us to find largest and smallest elements in an array. And this program utilizes a function named maxmin to accomplish this task. Now let's take a look at the prototype for this function here in the slide, the orange one. So in this prototype, the parameter A represents the array containing the elements we want to analyze, and the parameter n indicates the number of elements in the array, and the parameters integer pointer max and pointer minimum are pointer to integer variables, and these pointers will be used to store the addresses of the variables that will hold the maximum and minimum values found in the array. And on the bottom of the slide we have the example on how we can call the maxmin function. And by calling this function, we can efficiently determine the largest and smallest elements in any array. So in the maxmin program, when the function max_min finds the largest elements in the array B, it stores this value in the variable big by assigning it to pointer max. Similarly, when it identifies the smallest elements in the array B, it stores this value in the variable small by assigning it to the pointer min. And the program of max_min.c will read 10 numbers into an array and passes it to the max_min function and then prints the result. And so the program works by first it will prompt the user to enter 10 numbers, and once the user inputs these numbers, they are stored in an array, and then the program calls the max_min function and passes the array along with its size as arguments. Additionally, it passes the addresses of two variables, the big and small, where the largest and smallest elements will be stored. And inside the max_min function, the array is traversed to find the largest and smallest elements, and these values are then stored in the memory location pointed to by the max_min pointers. And finally, the program will print the result by dereferencing the pointers max and min to get the values stored in big and small. And this allows it to display the largest and smallest elements found in the array. For example, here if the user input the number in the red here in the slide, the program will output the largest as 102 and the smallest is 7. And now let's break down how our program works. So here we have first the includes the necessary header file, which is the standard input output header, and also defines a constant n with a value of 10 representing the size of the array. And then there's a function prototype for max_min, which is responsible for finding the largest and smallest elements in the array. And this function takes 4 arguments: the array A, its size n, and then the pointers max and min to store the largest and smallest elements. And in the main function, the program declares an array B of size n, along with integer variables I, big and small. And next, the program prompts the user to enter 10 numbers, and it uses a loop to read these numbers into the array B using scanf. And after reading the numbers, the program calls the max_min function, passing the array B, its size n, and the address of variable big and small. And inside the max_min function, the largest and smallest elements are initially set to the first element of the array, and then a loop iterates over the remaining elements of the array, updating max and min if larger or smaller elements are found, respectively. And finally, back in the main function, the program prints the value of big and small, which now hold the largest and smallest element of the array. And now let's try to run this program and see what's the output. So here we can see the output. The largest number is 102 and smallest is 7, like the one we have in our example before. Okay, next. So in programming, when we pass an argument to a function, we typically assume that the function might modify the value of that argument. So for instance, if we pass the address of a variable x to the function f, like this one in the slide, we expect that f might change the value of x. However, there are situations where the function f only needs to read the value of x without modifying it. In such cases, passing the address of x might seem unnecessary or even inefficient, especially if x requires a large amount of memory. And to address this, we can use the const keyword or constant keyword in the function prototype to indicate that the function will not modify the value of the argument. So the constant keyword is not only used to declare constants but also serves as a tool for documentation and preventing unintended modifications to variables. So when we use constant in the declaration of a function parameter, it signifies that the function will not modify the object pointed to by that parameter. So for example, consider a function here, function f that we have in the slide here, that takes a pointer to an integer as its argument. So in this function, the constant integer pointer p indicates that p is a pointer to a constant integer. And the constant keyword before integer pointer p means that the function f promises not to modify the value pointed to by p. And attempting to modify pointer p as shown in the comment wrong is an error and the compiler will detect it, and this ensures that the function behaves as intended and provides clarity to other programmers who may use or maintain the code. And in C programming, functions are not restricted to returning only simple data types like integers or characters. They can also return pointers. So consider the function we have here, function max, which takes two integer pointers a and b as arguments, and this function compares the value pointed to by a and b, and if the value pointed to by a is greater than the value pointed to by b, the function returns the pointer a. Otherwise, it returns the pointer b. And returning pointers from functions allows us to perform various operations, such as selecting a pointer based on certain conditions, and provides more flexibility in program design and implementation. And now let's analyze a call to the max function here. So in this call, we declare an integer pointer p along with two integer variables I and j. And then we call the max function, passing the addresses of variables I and j as arguments. And upon returning from the function, the pointer p will be assigned the value returned by max, which is either the address of I or the address of j, depending on their values. And consider the max function we just discussed, which returns one of the pointers passed to it as an argument. However, this is not the only scenario. A function could also return a pointer to an external variable or to a static local variable. However, it's crucial to avoid returning a pointer to an automatic local variable within a function. For example, the function f here we have in the slide, and this function I is an automatic local variable, meaning it's destroyed once the function f completes its execution. Therefore, returning a pointer to I leads to undefined behavior, since I ceases to exist once the function returns. And now let's explore how pointers can be used to refer to an array elements. So in C, pointers can point to individual elements within an array. So for instance, if A is an array, then ampersand A at index I represents a pointer to the element to the index of I in the array A. And sometimes it's advantageous for a function to return a pointer to specific element within an array. For example, consider a function called findMiddle, which returns a pointer to the middle element of an array A, assuming that A contains n elements. Here in the code, in the bottom of the slide, here the ampersand A at the index of n over 2 denotes a pointer to the middle elements of the array A. And I think that's all for the material. Here we have some exercises that you can do on your own, and if you have any difficulties, you can reach out to me or to Paulita. And now let's summarize the key points we have covered in our today's lecture. So, in C programming, programs often contain both local variables, which are defined within functions, and external variables, which are declared outside of any function. And every variable in C has a specific storage duration, which determines how long the variable remains in memory, and scope, which defines where the program the variable can be accessed. And pointers are variables that store memory addresses. They are used to locate the address of another variable in memory. And pointers can be passed as arguments to functions, allowing functions to modify a variable outside of their own scope. And additionally, functions can return pointers as return values, and this allows function to dynamically allocate memory or return references to specific data stored elsewhere in the program. And understanding this concept is essential for effective programming in C. And I think that's all from me. I hope you have a great journey learning C programming, and if you have any difficulty, just reach me out or Pawira. I hope you have a great learning journey and see you.